Today we will discuss what goes inside a modern computer system, right? So this course that we are studying is all about computer organization and architecture. Okay. And again, I am emphasizing this is the most fundamental and most important course of your curriculum because that differentiates between you and a typical engineer, software engineer that you find in the marketplace. Okay, suppose your friends from mechanical engineering department starts coding, uh, that's all anybody can do because computers computers in general present abstraction. Highest level of abstraction is programming language, or you can say applications, right? When you're running application, you don't need to understand anything excepting for GUI of application. The next level of abstraction is programming language, right? We call it high level programming language, like you have studied C or C++ or Python. So, however, what is below that level? What are the other abstractions, right? That you will come to know in this course. So, we will not touch anything about higher level programming language. We will not go into applications and so on. We will, of course, study programming languages in little detail and then see how these programming languages are actually implemented inside. Okay, how do you convert this high level language into machine language? Not really studying compiler, but what all conversions we need to do and how machine will execute that higher level program when converted into lower level program, right? So the level of abstraction there, we are going to almost like bit byte level in this course. So this is and we'll also touch upon few system level concepts. So this is very important course in your curriculum, and at the same time, it's very important when you do a job, right? I mean, you take up a job and uh, start working. This course will help you a lot in terms of your understanding of concepts. Okay. So today I thought we will discuss what is inside a computer that we use. Okay, and because I had to cover different components of a computer because that's the course. Okay, computer organization or what are different. So I thought why not take up a desktop, okay, and look at the technologies that it presents and then study it and then learn from it, right? So that is the approach I have taken. Instead of a desktop, you can also take, say, for example, a laptop or iPad. So maybe iPad or any portable mobile device. Possibly we'll take it up later because it has totally different design constraints. Okay, so today we will cover the following: processors, GPU. Now we will look at the very abstract level, high level, right? We'll not get into details. Okay, then the memory, buses, and network. That's all a typical desktop will contain. Of course, it will have a few other things which we will not cover. Say, for example, it will also have power supply, it will have keyboard, printer, and so on and so forth. So those things will not touch upon. We look at what goes inside a box, typical box, right? So what I have done is that I have taken, I looked at modern PCs and then I picked up one high-end PC, okay, from which is a Dell PC, okay, and then looked at its components, and I thought I will discuss these components, okay, all right. So this is so I picked up one desktop, okay, and then it looked at the spec sheet. It says the following thing: it has a processor. It actually has multiple processors. Okay, it has the processor reads something like it's a 10th generation Intel Core i9 10900K as a 10 core 20 M cache. Speed is 3.7 gigahertz up to 5.3 gigahertz. It supports 20 threads. Okay, it has integrated into the processor. It has an integrated GPU. Okay, and then it also, the board also has one discrete GPU. It's a separate chip set of GPU, right? Which is a separate processor, which is NVIDIA's GeForce. By the way, today the NVIDIA is in use because ARM, which contain a part of NVIDIA, has sold it to some other company. Okay, in the newspaper. Uh, so these are the processors in the desktop. Okay, and all of us, almost all of us that, and we are using laptop or desktop. If you go to its motherboard, and then you will see that it contains Intel processor. So Intel chipset has been very popular starting from 8086 till today, because most of the PCs use Intel chipset or AMD's chipset. AMD and Intel's are very similar, right? Because specs are the same and implementation. AMD is a different company, but it's a whole ISA, or instruction set architecture, etc., is exactly the same. Okay, all right. So these are the two processors. So if you buy any high-end laptop today or desktop today, it will surely have a general purpose processor, which is the first one. It will also have a specialized processor, which is largely for graphics. Okay, uh, so these two processors. Now, then I found that it has a set of memories, right? Different kinds of memories. So it had solid state drive. Wow, whatever laptop I have bought till today, never had solid state drives. And then it has hard drive, which all of us have in our laptops. Okay. Then we have, in this processor there is a storage accelerator. Well, this is also new thing, right? Intel Optane memory, also called a storage accelerator. Then all our laptops have DRAM, which is a main memory. Nowadays we are using DDR4, which is a type of DRAM memory. We'll look at this, right? And then in order to connect various parts of computer, we will also have buses. Okay, so it has a bus. Uh, all right, which is a PCIe bus. And then laptop today has interfaces for Ethernet. Okay, so you can connect cable. Okay, and from that cable goes to a router. Okay, uh, okay, lower end of the router always have Ethernet, right? And it also has Wi-Fi ports, right? And there are large number of Wi-Fi interfaces a desktop or laptop today supports. Okay, if time permits, we will go into these in one of the lectures, how Wi-Fi actually works and how Ethernet works. But I'm sure you would have touched Ethernet in your networking class, and also Bluetooth, right? Um, I'm sure you know the difference between WLAN, that's Wi-Fi, and Bluetooth. Okay, if you're not covered, then we'll briefly touch upon these two. Okay, not in this class, but later. And also it has good number of ports, right? Like USB port or headset port and RJ45 port, which is for Ethernet. Audio input output line, right? I mean, you can connect your, like I'm connecting my mic and microphone into my laptop. So there is a port for that. And there is a sensor here, temperature sensor, a battery sensor, fingerprint sensor. Okay. In case you are using your mobile or iPad, the number of sensors are much higher. It has about 15-20 sensors. Okay. Desktop will have very few. Laptop will have slightly more than desktop, but mobile phone and iPad have just too many sensors. Okay, the question to you is that have you ever looked at specification of your laptop?
Yes,
Is
sir.
it,
And my
yeah,
laptop is pretty old laptop, 6 years old.
yeah, that's
Even
fine.
though Yeah, even though it has i7 third generation,
Okay, great.
it
So
has,
just
yeah.
just go through complete spec because there's a lot of learning there. Okay, and go through the latest one. I would suggest that go to latest desktop or laptop and then see what it contains, right? Then you can trace the path. Okay, you can also see, what kind of software it supports, also what kind of drivers it has. We'll cover some of this in the class today, all right? And then try to learn from that, and then something that we don't know, we'll cover in subsequent classes. Uh, let's go to the first part, right, which is processor. Okay, and please feel free to ask questions at any point in time. I'm very happy if you ask questions because it gives me opportunity to learn. If I don't know, I will learn. If I know, I will help you in learning. Okay. Because these all thing that I'm presenting is very latest because this whole desktop was has come uh, has come to the market just few 1 or 2 months back. So and technologies are changing very fast. Okay. So let's go into processor part. Now the first this all specification is there. Then I went into the product detail and got other numbers. Right, it's a 10th generation Intel i9. Okay. Now when you look at Intel progression from first generation to last generation, they have changed the processor architecture continuously. It means the interface to all that is ISA, instruction set architecture, right? So whatever instruction set they had in the beginning, they have to support that because a program that was written 15 years back for Intel processors must run even today. Okay, while technology has moved from 16-bit to 32 bits to 64 bits, uh, ISA, something that's written for 16-bit has to execute even today. Also, it means that their instruction set has continuously changed. That we'll study later. Okay, but beauty of Intel architecture is that program that was written 20 years back can still execute on your laptop, right? And there's a beauty. Okay, now that creates a lot of mess also. We'll look at the mess little later. Now it has 10 cores, right? So number of cores are 10. It means that 10 processors are embedded. Instead of having one large size processor, it has 10 processors interconnected to each other. Okay, and number of threads that it supports is 20. It means that on each core we can run 2 threads. Okay, what is a thread that you will study a little later? I mean, you can think this as a lightweight process. Okay, uh, now the question I can ask you: who allocates work to this course? Is it compiler? Is OS? Okay. Second thing is that do they run independent task or part of one task? A thread may run part of one task, other thread may run different part, and so on and so forth, right? That we have to also see. And what is the role of compiler here? I mean, see, you're writing program in Python or C, right? You're not so your understanding is limited only to higher level language. You don't know about anything about what goes inside, and that's true for large number of software engineers. I would think 99% software engineers don't know anything beyond the abstraction that's presented to them. But then compiler has to be smart enough to do certain things, right? Because inside is good number of processors and parallel processing capability available, right? So one compiler has to create a code which can run parallelly. Okay, so what is the role of compiler? What is the role of programmer? Can you help? Right, so now here I would like to give little details. See, over last 40 years, Moore's law has presented itself beautifully that you write a program today, compile it, run it, create an application if you want, and then next year is or its performance goes up because there are faster processor available. After 2 years, the speed doubles, so your program keeps on executing at faster pace. Okay, it means that in 30, 40 years time, your processor speed has gone up by more than that. Or we can say in last 20 years, processor speed has gone up by 20 times. So your program also executed 20 times, and that free lunch is over. Now, Moore's law we discussed earlier is slowing down. Okay, slowing down in the sense still more number of transistors coming inside chip, but the rate at which this increase is happening is reduced. And there are two limitations. One of that we have studied earlier is because of the heat, we call it power wall. And second limitation is because of the memory. Okay, the speed of memory. So it's called memory wall, which we'll touch upon later when we study memory. So because of these two, uh, we can't have very powerful processor, but we have multiple processors. Okay, the role of programmer is now very important to write program appropriately such that it can run over multiple processors or multiple cores. Okay, that will so and you have to see that can you write multi-threaded program? If you cannot, then whose responsibility is this? All right, so these are the questions which we'll answer not today, but during the course. Then it has 20 MB megabyte. When we write capital B, it is byte. When you write small b, then it's a bit. Huh? So it's a 20 megabyte built-in cache. Now cache is a memory which is fastest possible memory, and it's a small size in memory. It's small size memory. Generally, it's made of SRAM. Okay, static RAM, and then is capable of operating at highest speed. Okay, usually it has 6 to 8 transistor per memory cell. Okay, so it's very very fast. So whatever instructions or data you are using frequently, you keep it in that cache. Okay, it's like I mean, at your home, if you have thousands of books, but on your desk you read, you have the 4 or 5 books which you use very often, right? So that your time going up to your personal library and bringing a book reduces, right? So similarly here in cache, you keep only something that's being used frequently. Okay, we'll look at the cache architecture a little later. Okay, then what does main processor contain? Now, when I look at the specification, it says thermal design power. Now, we touched upon this in earlier lecture, right? So it says that it has thermal design power as equal to 125 watt. It means that it is average power the processor dissipates when operating at the base frequency with all cores active. Okay, given one workload. So Intel has defined its own workload. It means that set of programs. Workload is nothing but set of programs running on different processors. And when it's running at the base frequency is defined as 3.7 gigahertz, then the power it consumes is 125 watts. So this is kind of base power, we can say. It's kind of uh, some kind of measurement they have set in. Okay. So base processor frequency is 3.7 gigahertz, but the maximum frequency it can go up to is 5.3 gigahertz. Okay. Now it means that at TDP the frequency is 3.7 gigahertz, but now if let's assume that only few cores are running and each core is not running at full capacity, then you can always measure the heat and then increase the speed as much as you want, such that as long as it's within some limit. Okay, so maximum speed that it can go up to is 5.3 gigahertz, and it has to be dynamically changed looking at the state of the system. All right. Okay, so basically what we have studied earlier also in last class, that processor operates at set of frequencies. So different cores can operate at different frequencies depending on the requirement. If the workload is small, then the processor need not to run at maximum capacity. When, for example, you are just listening music or doing word processing, then processor doesn't have to. But if you're playing video game, then it has to operate at highest possible frequency. Otherwise, it will not be able to do complete its task. So now computer adjusts this dynamically, and each processor we defines two frequencies, lower limit and upper limit, and depending on workload and other system parameters, frequency can be increased or decreased. Clear? All right. Next, I found that it has GPU. Okay, it's NVIDIA is a company that makes GPU. This one of the few smart companies. And then it has RTX 2070 Super 8 GB GDDR6. Okay, then I thought let me look at what GPU is, that what's the base functionality, and then we will build upon that when we have at least one or two lectures on GPU. Okay, now to give you concept of GPU. Okay, CPU consists of only few cores. Okay, central processing unit or the main processor consists of only few cores, optimized for general purpose calculation, right? Because it's a general purpose computer, like your PC is meant largely for general purpose computation, whether it's a word processing or listening to music or browsing a web or whatever. Okay, so we have concept of central processing unit consists of general processor for general purpose work, and then we attach to that specialized processor. Okay, very specific purpose processor, which we call as GPU. Okay, so you can always think of GPU as a specialized processor. And now GPU is largely designed for certain applications. Okay, largely graphics, high-speed graphics like video games or AI nowadays, or TensorFlow analysis or weather computation and so on. Now, the basic feature of all that is that instead of one large size processor, it has to have large number of processors, and each must be doing similar task, say matrix multiplication or something else. But number of places where this multiplication has to happen has to be in thousands. Okay, so 1,000 parallel processors can do a particular task, which is highly compute oriented and repetitive task. Okay, so GPU consists of hundreds or thousands of smaller efficient cores designed for parallel performance, and hardware designed for a specific calculation, whether it's a weather forecasting or it's a high-speed video games or it's a TensorFlow analysis or matrix multiplication or something else, right? All right, like for example, Tesla, I'm sure you all know about Tesla's car, right? Has designed for its own use a GPU. Of course, it has come out with the help of NVIDIA. But today, if you look at all these companies, okay, whether it's a Google or is Amazon or Facebook or Tesla or any other, they are all have their own designs of GPU for specifically meant for the applications that they are running. Okay, and you go to Google site and find out what GPU they have designed. Similarly, you go to Amazon site and find out what GPUs they have designed. Okay, now GPUs in general, we can say, are designed for very specific application. Okay, so you have a PC wherein you have CPU, and then you will also get various kinds of GPUs. Okay, and then usually in a desktop there is a one particular kind of GPU. All right, any question? Okay, let's move ahead, right? Okay, so what you'll see here, picture shows Intel Xeon E5 GPU, which has 64 cores. Note that this is only for general purpose computation, and memory size is 256 GB, and bandwidth is 76.8 GB per second. But the bandwidth is, this is the data bandwidth. It means so much of data can pass on per second. It's related to its I/O port speed and so on. Okay, now this what figure I'm showing is not corresponding to the processor we are looking at now, but in general, because I want to tell you the concept. This is largely for application called single chip cloud. And similarly, this NVIDIA's Tesla P100 has 3840 processors or cores. Okay, these are of course single processing floating point operations, right? Memory is 16 GB. So you can, now difference you can see is that memory is less here. Okay, because it is more compute intensive application, right? And bandwidth, you can see the bandwidth here is low, while bandwidth here is very high because each processor has to transfer data to other processor or somewhere else, depending on the type of computation is doing. Okay, so in general, GPU, we can say number of processors are at least 300-400 times, or at least 100 times that of a normal CPU. Memory size is smaller, but bandwidth is very high. Bandwidth is nothing but data rate. Total data rate of GPU is, say, I see at least 10 times or 7 to 10 times that of a CPU. Okay, all right. So now let's look at an application code. It has two types of computations. One is general purpose computation and one is compute intensive functions, right? So what processor can do is that, of course, compiler has to do that, and also OS role is also there, that something that is compute intensive will go to GPU and something which is normal sequential CPU code will go to CPU, and then the results from both are received and then total output is presented. Okay, any question? All right, let's move ahead. Okay, so this is the specification of the GPU that I found in this Dell desktop. Okay, so it has number of cores as 2560, is quite high, and it can run 52 tera operations. Okay, we are not going to detail because what NVIDIA has done is that they have presented their own way of calculating the speed in terms of certain kind of operations, which they call as RTX operations. Okay, we'll study this later. And then they have also defined what is gigares. I mean, if you have done some course on graphics and related topics, then you would have come across these terms. It has base clock of 1770. The boost clock is 1605. We'll look at these concepts later. Memory speed is 14 gigabits per second. Okay, this is actually a bandwidth. All right. So this is a GPU that the desktop uses. Now, obviously, desktop price cannot be very high. It should be about $1,500 or $1,000, close to 1 lakh of rupees. So the GPU for it will be of limited capability. But in market, you can find out GPUs which cost as much as say $1,000. Okay. So it has RT cores, which is nothing but ray tracing hardware. Ray tracing is essentially used for graphics applications, features, for example, shadow, reflections, etc., and tensor core. And it has also tensor core, which is for AI processing. All right, so we looked at GPU in general. Processors today or computers today have CPU and GPU. CPU has few cores, GPU has thousands of cores. GPUs are used mainly for parallel operations. I mean, a task which can be split into subtasks and each subtask can run on a processor. That kind of computation we can do it on GPU. Okay. All right. You any question on GPU?
Sir,
Yeah.
I have a question. So, what is the
Yes.
difference between the integrated graphics and the discrete one or the dedicated graphics?
Okay, so what happens is that when they design chipset, so within that chip, they think that even a sequence, some tasks that we do will have some graphics or some operations which can be done parallelly. Okay, so now most of the processor makers have started building a small GPU that's embedded in the same chip as that of a main CPU, along with the cores, other general purpose cores, right? So this is very the one which is integrated, which I'm showing here, is built into the main chipset. So now it is your choice to have a external GPU or not. For example, my laptop here, which I am using, which is Apple's laptop, doesn't have GPU. Okay, so now I have a high precision screen on, or when we are running, I am running video, then all this video computation can be done on built-in GPU, not the disk. Now, if I have a very specialized application, right? For example, I am running TensorFlow analysis or video gaming, right? Then my GPU, which is built into it, integrated GPU cannot handle this task. Hence, I need for specifically for a particular application, very specific GPU. Okay, got it?
Yes, ma'am.
Okay, so now one simple exercise you can do is that you find out what are different kinds of GPUs available for specific applications. All right, and one thing that is becoming very clear today, that when the most of the applications that we design are data sensitive, right, or data heavy. Okay, like you do any AI applications or data analytics applications or weather forecasting applications or whatever, right? So most of the applications, because data is available enormously, right, around us, and so far we have using general purpose computers, okay, like your PC, to do all these applications. Now, PC is not designed for an application. It is designed to run a set of application, and performance that we get is also average performance, right? Now, when we are running very specialized applications, then new way of designing computers today is becoming hardware software co-design. Looking at the software, you are designing hardware that will suit the application. Okay, so we will possibly touch upon this concept of hardware software co-design and how to design hardware looking at the application. Okay, now step in between is having a general purpose processor and attached to that a GPU which will do very specific kind of task. So this is not the final solution, this is a solution in between. Okay, all right. Good that you asked this question. Next component that I found in desktop is memory. Of course, all of us know about memory, right? I mean, laptop has hard drive, and hard drive has been there for a very long time. Okay, before, in fact, not many of you would have seen the floppy drive. I started with floppy drive and never had hard drive, and then before that, still organization used tape, magnetic tapes. Okay, so magnetic tape capacity is 500 terabyte and so on, right? So uh, we'll not look at magnetic tapes and floppy drive, etc. We'll start with hard drive. Okay, the hard drive that most of the laptops today is close to 1 or 2 terabytes, right? And is a mechanical structure, right? It's non-electronic device. Okay, it does not contain semiconductor technology, right? It's mechanical. Uh, okay, it means that now hard disk has to rotate and we have to read something from that. It's like LP or earlier we had these records, right? I mean music records. Uh, that kind of record it uses. It's the same technology. Okay, so let's look at this in brief, right? So this is what your hard disk looks like. Okay, the evolution has been ST506 up to SATA. Okay, so these here are the plates, okay, or we call it platter, and on that there are concentric circles. So first circle, second circle, third circle, fourth circle, and so on and so forth, right? And in this track, we divide this into sector, and in each sector we write data. Okay, now advantage of this is that it's enormously cheap, and life is quite long. Okay, but at the same time, it's a mechanical, right? There has to be motor and that will rotate this, and these are the heads. Heads will you'll place over the track that you want to read. So disk has to come to right position where you can read. It means that if your head is here, you'll have to move head to right track, and then it will rotate, and then you will have to start reading from particular sector. Now, good thing also is that it has multiple parallel heads, so you can do parallel read and write. Okay, now most of the time we don't use parallel read and write, but from one track we get the data. Okay, we'll discuss this a little later. So what is it good for? It's good for most of the machines because it is very cheap and it's non-volatile, right? Once it means you can read and write, and on reading the data is not lost. It's non-volatile. So it is suitable for loads that are largely sequential and not performance sensitive. So most of the things that we do, reading a say word processing file, Microsoft Word file, it doesn't matter. It takes millisecond or a nanosecond for us, right? Because when we human beings are working on something, we cannot observe that difference, right? So it works out fine for me as long as it's cheap, right? So it's very cheap. Lowest among all storage technologies, says the lowest cost per GB of data. Okay, and then sizes are increasing. It's becoming smaller and smaller. You can think my iPad contains a hard drive. It earlier used to contain, right? Now my laptop contains a hard drive. Okay. Sizes are decreasing, all right. It is becoming smarter also, right? So inside this also we can have a small cache. Cache is something that is, see, for example, you're reading a data from, you're reading only 1 byte, okay, or 1 word. So instead of 1 word, you can cache number of words into local cache here, because what happens is that it's very likely that next word will also be read, right? So based on locality of usage, we can cache the data into local cache here inside this. So we are not talking about processor cache. We are talking right now about cache here that's inside. Rotational speed is 7200 revolutions per second. Now access time, if you look at it, 6 to 15 millisecond. Now it's slow from computer perspective, right? CPU works at very fast speed. Okay, and when you have multiple cores and then doing I/O requests, then you need a much better bandwidth. So it's 200 times slower than a main memory, which is a DRAM. Okay, all right. Any question?
So could you please repeat what you said about read and write caching?
Read and write.
Caching.
Okay. Something that is not shown here is there is a small cache memory. Okay, so cache is basically a small memory area which consists of high speed memory. Okay, cache here will not consist of this technology here, but it will consist of some semiconductor memory which is kept inside a disk drive. Okay, and something that you are reading. For example, you are reading this particular sector. Okay, some information. So it's very likely that you are going to read, next instruction or next data, which is on the same track. Okay, so what will happen? You say that I want to read 1 word. That 1 word, of course, will be read and sent to CPU. Okay, now when you say I want second word, again same process will repeat it. because your head has to come to second word and then word has to go. So instead of that, if you want to reduce time, then you can guess that, okay, not only word, but maybe 100 words will be required. And let me put these 100 words into a memory at the interface, which is faster than this, which is semiconductor memory. Okay, now when the next request come for the next word, then instead of looking here, you can look at the cache, which is inside this box at the interface, and you send the data from there. So you save on overall, in terms of time. Okay.
Okay, sir, got it.
Now, cache consists of high-speed memory, semiconductor memory. This is a magnetic memory, which is slow. So items that you are going to read frequently, instead of putting them, by reading them sequentially from the platter, you read it once when you're reading the first information, put number of read it sequentially and keep it somewhere, hoping that this will be used frequently. So that way you can reduce the access time. So cache in general is a concept. A system will have multiple level of cache, starting from slowest possible device, which is hard disk, going up to semiconductor memory is a main memory. On top of main memory, in processor, we also have a cache. So something that we are using very frequently, like you are doing, for example, you're doing word processing, right? And word processing, you're using the same data repeatedly. Then you don't have to bring the data every time from the main memory or from a hard disk up to to processor every time. You don't have to do that every time, but you bring it at one shot, set of data items which are to be used very frequently. Okay, so once you have data available, which is small in size, closest to processor in the fastest possible memory, and this fastest possible memory or the cache that is with processor is at least 10,000 times faster than your hard disk. Then you achieve the speed up. Okay, so we'll read the cache concept little later, but cache has become, this concept can be applied at different level, right? So for here, when we say built-in cache, it means that in the box you get this drive, and within that there is a small cache which will cache the data items locally from here and present it to top if required. Okay, got it?
Yes, sir.
Understood?
Yes, sir.
Okay. Okay, let's go ahead and see what is solid state drive. Have you heard of this terminology? I'm sure you are using this.
Yes, sir, we have heard of this.
Okay, what is it? Are you using it?
Yes, sir.
Yes,
My
sir.
laptop also has 256.
Okay, fantastic. Your laptop must be recent and expensive one. Okay, but all of us do use flash drive, right? Flash drive that you can put into USB, flash stick. Okay, flash stick, all of us use, and it's the same technology as a flash. Instead of single flash of 100 GB or 50 GB, you have set of these chips put together, and that creates solid state drive. Okay, so now here there is a motivation. See, your spinning disk are excellent, though it's an old technology, it's a mechanical technology. The CPU and RAM at gigahertz. Okay, then we have Ethernet buses that also operate at gigahertz or gigabit per second. Okay, but the hard disk access time is 6 to 15 milliseconds. It's very high. Okay, so we of course have got to have disk, but we can also have memory which is non-volatile memory, where access time is faster, right? So that something that can sit on top of spinning disk is these flash drives. Okay, so many laptops don't have hard disk, but only flash drives. Okay, and flash drive technology is also improving, but still is not perfect at this point in time, right? So I'm sorry. Here is a solid state drive. It's a non-volatile memory. It consists of flash chips. Okay, and the basic technology here is a NAND gate, or it's called NAND flash memory. Okay. All right. So we have at the bottom this kind of disk, which is a hard disk, and then next level is solid state drives. Okay. Um, this is a flash memory chip, and then the way we store data in the flash drive is very different, right? It's non-sequential. So what you do is that if suppose you have a 32 or 64 byte data, then you strip it out into multiples. Okay, so for example, each chip will contain, say, for example, 4 bytes. Okay, that way you need, say, 64 by 4, that is 16 different chips to store 64 byte data. Okay, so basically the basic data, suppose you are reading a file, then and you are reading within file some portion, say 1,000 bytes. That 1,000 bytes will not come from the single chip. It will come from parallelly. It will come out from multiple chips. Okay, what's the advantage? Of course, you reduce the access time. Okay, rather than reading them sequentially one after other, because in that case you have to dependent on the bandwidth of that particular chip. Like your flash drive you put into USB port, there is a certain speed at which it can work, right? Okay, here you can do it parallel read or parallel write. The disadvantage of this is the reliability. If one chip goes off, then whole data goes bad. Okay? However, this technology is improving. All right. Advantage, disadvantage. Advantage is, of course, access time. Cost is more than hard drive, but it's changing fast. Okay. It's almost like 50 to 100 times more expensive than hard drive in terms of bit rate, in terms of per bit cost. Okay. I'm sorry, it's almost 10 times now, not 100 times, 10 times. Failure rate is lower than that of a hard disk drive. The hard disk drive is mechanical, right? Something can go wrong, right? But SSD is all semiconductors, so failure rates are smaller. However, the access time is the huge difference. It's between 20 to 100 microsecond, wherein hard disk drive is 100 times slower, right? So essentially it is, if you compare, the access time is around 20 millisecond for SSD, wherein is 400 to 500 millisecond for hard disk drive. So almost like 20, 30 to 100 times faster. Of course, this picture does not show 100 times faster, but in general, that's how it is. Okay, any question?
Sir, hello, sir. So, in the
Yeah.
previous slide, what is the meaning of non-volatile memory?
Okay, so basically, you have RAM, right? Random access memory, which see, your processor reads most of the data from cache and RAM, random access memory. Both are semiconductor memory, wherein whenever power goes off, the data is deleted, right? Or data goes off. It loses the data. Okay, so memory are basically of two types: volatile memory and non-volatile. I'm sorry, I thought you guys know that, but I'm sorry. This basic concept that memory is of two types: volatile and non-volatile. Say when you boot up your laptop, right? Then data comes from non-volatile memory. Your boot sequence, etc., OS, etc., comes from either flash or hard disk. Okay, when you write something that you don't want to lose, say for example your file or video file or something, then it goes to your hard disk or flash memory, mainly hard disk. Now while doing computation, when say for example you're doing word processing, uh, of course you have a copy in hard drive. Okay, but sometimes power goes off and you lose everything because your file or the changes that you have made is in file, part of the file which is in cache or main memory. So main memory and cache, they are volatile, and then your hard disk and solid state drive are non-volatile memory. Okay, got it?
Okay. Yes, sir.
Okay. I'm, it's good that you asked this question because I assume sometimes you know all this, right? But please feel free to ask. Okay, and then last year, Intel has come out with a memory which is called Intel Optane Persistent Memory. It's a non-volatile memory. Its access speed is faster than that of uh, your the solid state drive. Okay, and it means that access speed is faster and the cost is likely to go down, right? So when you make this triangle, lowest level is hard disk drive, which is cheapest but maximum capacity. Next is that solid state drive, okay, which is little lower capacity than hard disk drive, but access speed is higher. Then you have now this a new memory that has come out, which is called Optane persistent memory. I think you won't have heard of it because it's very recent. Only latest processor like the one which we are discussing has it. And then on top of that, you have main memory, which is DRAM, or we call it SDRAM. Okay. So as you go up, you have faster and faster and faster memory. And when we'll study memory hierarchy, we'll see how all this operate. And on top of this, that is not shown here, is a cache memory. Okay, processor cache memory. And we have multiple levels of cache memory. Okay, when we say internal cache, that's nothing but processor cache, something that's in processor. However, we have seen that in HDD also there can be a small cache. Okay, now the technology for this, technology for example, for HDD is magnetic. This is semiconductor. This also is semiconductor. However, it uses something called phase change technology. With the phase of the material changes, and you can sense that. Okay, have you used this technology in the past ever? Phase change technology? See, other technologies are based on charge. For example, DRAM is based on whether capacitor is charged or not. If it's charged, then it's 1, it's not charged, 0. Okay, magnetic is that part of the magnetic bit is space is charged or not charged. If it's a magnetic charge is there, is 1, otherwise 0. Here is nothing but phase change. Okay, and one technology that used in the past phase change was read-writable DVDs. Okay, now of course we don't have DVDs in desktops, but DVD has been very popular technology. And then in DVD came, last about 10 years back, 15 years back, this technology came where you can write over DVD and read it also, right? It's changeable. Wherein earlier DVDs were only readable. So when you can read something from write into DVD, that used phase change technology, and it was optical technology. Okay, so we are not going to discuss that. But the advantages of this Intel Optane persistent memory is 15 to 20 times faster than I'm sorry, 10 times faster than SD drive, which uses NAND memory. Okay, and is less expensive than DRAM. Okay, all right. So it looks something like this. Okay. Let's go into next one. How much time we have? Okay, another 2-3 minutes. Uh, okay. So this is, so in general we have the following things, right? We have GPU, we have processor and caches, and then all these use main memory. So processor is connected to main memory, okay, and then below that are other memories that we have seen, say hard disk drive, and then we have SSD and so on. So main memory is something which processor accesses most of the time, apart from cache. Okay, so it consists of, it is mainly the technology that we use is DRAM, or we call it SDRAM or synchronous DRAM. Okay, where access speed is faster than other memories, which is 60 to 100 nanosecond. Okay, an advantage of this DRAM is that it's a very simple technology, right? You need just one transistor and one capacitor to create 1 bit memory. So it can be very high density. Okay, however, there are some problem with DRAMs. That's the reason the scalability is issue. We'll look at this later. So main memory in general will look something like this, that we have here we have DRAM chipsets, okay, and that's connected via some interface, okay, and there are multiple cores will share this DRAM. Now, see, today understand, we don't need to understand everything about all these technologies today. This presentation or class gives you only the top level view of these technologies, and the whole semester we'll study all this, okay. If you don't understand anything, please note it down and we'll study that. And then we have bus. Let me just take 1 more minute and then close. And buses are required for IO transfers. Okay, so we'll, and then bus that this PC uses is called PCI bus. We'll study this later, and in next class, that's tomorrow, we'll study structure of this, and then we'll look at Ethernet and wireless LAN, and then we'll conclude. Okay, all right. We are almost done, excepting for 2-3 slides, and then following class we'll look at some other things, right? Okay. Now, one question I have to for you is that, are you finding the pace very fast? Are you able to understand it? Because I am using these terms very frequently. For example, main memory, cache, SDRAM, DDRAM. So it takes time to understand all this, right? So this lecture is essentially to give you top level view. We are not going to detail, but if you can understand little bit about it, is good enough. Okay, and because we will go into each of these little later and then spend some time. Okay, meanwhile, what you can do today is that look at spec of one of the latest computers and see what it has. Maybe you'll find different things out there. Okay, all right, thank you.